Hi folks, thank you for joining me in this video about limits involving Pythagorean identities. So sometimes a limit can be simplified by using a Pythagorean identity. Fortunately for us, the only Pythagorean identity that must be memorized is sine squared theta plus cosine squared theta equals 1. So to derive the other two needed formulas, divide by sine squared theta and get the result, and then divide by cosine squared theta and get its result. Now, you won't always need these other two theorems, but if you have this one theorem, you can find the other two just in case you need it in any other problem. So we'll divide both sides of the equal sign by sine squared theta. We learned that we can do algebraic steps like that to each side of the equal sign, and it remains balanced. So sine squared over sine squared is 1. Cosine squared over sine squared is tangent squared. Cotangent squared. That is one of those identities that you'll need to know also. Cosine over sine is cotangent. And then 1 over sine squared is cosecant squared. So it depends on the situation what formula you want to memorize. I typically remember this one. 1 plus cotangent squared theta equals cosecant squared theta. However, it might also be beneficial to memorize it as cotangent squared theta equals cosecant squared theta minus 1, which is just the algebraic equivalent. Okay? So I typically, like I said, I typically memorize, I just memorize sine squared plus cosine squared equals 1, and then I just derive the formula if I ever need it. Okay? So now what we're going to do is take that same formula, sine squared theta plus cosine squared theta equals 1, but this time we'll divide both sides of the equal sign by cosine squared theta. Now, when we divide by cosine squared theta, we'll have sine squared divided by cosine squared, and that gives us tangent squared. So tangent squared theta plus cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared theta. And again, this is the way I typically memorize it. However, you might need to use it with the formula kind of looking like this. Tangent squared theta equals secant squared theta minus 1. All right? So there you have it. Those are sine squared theta plus cosine squared theta is the only Pythagorean identity you need, and with that one, you can derive the other two formulas. Now let's look at some examples dealing with the Pythagorean identity. Zoom in a little bit. So this time it says we're going out to 3 pi halves. So the first thing that I want to try is to see if I can substitute it in. But cosine at 3 pi halves is going to be 0. And at 3 pi halves, this would give me actually -1, but I'd have 1 plus -1, so 1 minus. So basically, I'm getting 0 over 0, which is an indeterminate form. Now, what are we going to do with that? Well, I notice that I have this cosine squared at top, and this is the Pythagorean theorem page. So maybe we'll try to use that Pythagorean identity. So instead of cosine squared theta, what if I rewrote it as 1 minus sine squared theta? Which is basically just the algebraic equivalent to our first theorem. If I had sine squared theta plus cosine squared theta equals 1, then I could just subtract sine squared on both sides to solve for this cosine squared. Okay, so cosine squared is 1 minus sine squared, and this is really close. Okay, now what I'm going to do is I'm going to use the difference of squares factoring pattern. The difference of squares factoring pattern says that a squared minus b squared, maybe I don't need the parentheses there, but it equals a plus b times a minus b. And you can see how this is going to give us a pretty good result, because I'll have 1 plus sine theta on top and bottom, and that'll help me cancel it out. So we've got the limit as theta approaches 3 pi halves of 1 plus sine theta times 1 minus sine theta all over 1 plus sine theta. So what we can do there is cancel out the common factor on top and bottom. And once those cancel out, now we're to the fun part. We can actually substitute in 3 pi halves. So this is basically just 1 minus sine at 3 pi halves. Well, sine at 3 pi halves is -1, so this is essentially 1 minus -1, which will give us 2. Okay. So that one's pretty nice. So let's take a look at the second one, the second example here. Looks like the same kind of problem, doesn't it? So it hasn't changed very much. There's a minus sign here, and maybe we're going to pi halves instead of 3 pi halves. So we'll put the pi halves in, and I get 0 over 0, which is an indeterminate form. So then that means that I'm going to try to rewrite this expression so that it's equivalent. And once we write the equivalent expression, we're hoping that some kind of factors will cancel. Well, if we've memorized that cosine squared is 1 minus sine squared theta, then we're still in a pretty good situation here. We have the difference of squares on top, so we'll say that the limit as theta approaches pi halves. We have 1 plus sine theta and 1 minus sine theta and 1 minus sine theta on the denominator. So then we're just going to find, we're going to cancel out this 1 minus sine theta, and then we'll put in this pi halves. Now sine at pi halves we know is 1, so this is basically just 1 plus 1, and our final answer will be 2. Alright, so that was another pretty simple question. But the thing is that I've gotten the answer of 2 for both answers. So I know that the answer is not always going to be 2, right? So let's go ahead and work on this third question where it looks to be a little bit more confusing. Now when I substitute in pi halves, I would get 3 minus 3, which is 0. And I would get 2 times cosine at pi halves. Cosine at pi halves is also 0, so 2 times 0 is 0. So I'm getting an indeterminate form again. So this time though, it looks like we have a little bit of factoring to do before we use the Pythagorean theorem. So it's not that hard of a factoring problem, but this time we just take out a 3, and now we're left with this 1 sine theta. And then we already had a 2, and we have cosine squared theta. Now that I've done this twice, I don't think I need to show the work for this anymore. I think I have this one memorized. So instead of writing down 1 minus sine squared theta, I'm going to go ahead and factor that into 1 plus sine theta and 1 minus sine theta. And I hope that I've convinced you over the last 2 examples on why that is the correct factorization for cosine squared theta. So we're going to eliminate the factor on top and bottom. We are going to substitute in pi halves And when you substitute in, you do not need to write the word lim anymore. So we'll write 3 over 2, 1 plus, now sine at pi halves is actually just 1. So our final answer will be 3/4. Okay. And you can validate that with maybe a graph of this fraction here and go out to pi halves. You can push trace pi halves and see where we are. You should get the 3/4 as your y value. Actually, it would actually give you a, that's an interesting point. If you did type that in a TI-84, you would actually get nothing that shows up at pi halves. So then you would have to take a right-hand and left-hand limit if you were just looking at the graph. So option 4, or number 4, example 4. We have this secant thing that has shown up. Ugh, booger. Now secant, though, is the same thing as 1 over cosine. So secant squared would just be 1 over cosine squared. So if we're using that rule, this problem actually looks very similar to our previous 3 questions. Okay, so we're taking the limit as theta goes out to pi halves. The numerator is then going to say 1 minus sine pi. I'm sorry, I said the wrong word. 1 minus sine theta. And the denominator is going to actually just be cosine squared. And this is feeling a lot like number 2, isn't it? So number 2 was the exact same expression except it was flipped. So let's finish this one up quickly. Now the factoring pattern for cosine squared is actually 1 plus sine, 1 minus sine. So forgive me for not saying theta on each one of those, but it's 1 minus sine theta on top. And then the factoring pattern for cosine squared theta is 1 plus sine theta and a 1 minus sine theta. Okay, so we'll cancel the 1 minus sine thetas. Once those are canceled, you'll drop the pi halves in. But this is a big mistake that people make. People forget to leave the placeholder, that 1 on top. So let's not forget that. This cancels out to be a 1 on the top because these are factors and they cancel. And then I have a 1 plus sine pi halves on the bottom. And of course sine pi halves is just 1. So 1 over 1 plus 1, that'll give me 1/2. All right? So all of these have some kind of removable discontinuity, and that's what allows us to cancel these fractions out, or these factors out. Okay? So I did my best in teaching you guys limits involving Pythagorean identities. Please do your best to try and learn it so that we can move forward. Thanks a lot. Have a great day.